Now let's cover briefly cover time-independent approximation methods. Well, just one of them. We'll just mention another one afterwards. This is the variation method, which depends on the fact that for the quantum system, the expectation value of the energy evaluated for any child function is always greater than or equal to the exact state of the system. Now let's do an example. Sorry, I got indigestion here, I think. We'll take the potential energy function, V of x here, which is pretty much always a Coulomb potential we're dealing with here. It's always spherically symmetric things, atoms and whatnot. For any infinite 1D well, oh, sorry, no, this won't be spherically symmetric in this case. This is a unrealistic one-dimensional model, but anyway, the kind of point still stands. From the Schrödinger equation here, which should be abundantly obvious by now, this is the Hamiltonian operating on this wave function, which will give an energy of the wave function. That's Schrödinger equation basically in a nutshell. We obtain an expression for E of n, which is an energy level in terms of the eigenfunctions, by taking the inner product of both sides of the equation with the eigenfunction psi of n. So here, and we rearrange to get E of n here, and which is the method we're going to use here, which is a variational method, which I wrote, which is the method. Yay. Back to the example. Choose a psi of 1t equals L squared over 4 minus x squared. This is not normalized or anything, it's just for an example, so it will suffice just to demonstrate. And plugging this into this formula here will give us this, and which when solving will give us this as our energy state. And we know this this value must be greater than or equal to the ground state. We could also use perturbation methods. I think there are various other methods, perturbation methods, things like that. And like these kind of small corrections, they're very important in applied mathematics. In for example, general relativity. If you're doing general relativity, we have things like Christoffel symbols. I'll cover all this in some later date. And that's those correction terms, I think, are to do with how the space-time distorts, or something along those lines anyway. But I'll come up to that at some point. I'm going off on another tangent here, but yeah, we can use first order approximation methods with with the nth eigenvalue. In the first order perturbation theory, the nth energy eigenvalue is approximated here, where En of 0 is the nth unperturbed energy level and delta H is the perturbation, and this here is the nth unperturbed eigenfunction. All of these quantities on the right hand side we know or can be found by solving the unperturbed time independent Schrödinger equations. These methods become increasingly important when we deal with atoms heavier than hydrogen. Thus we have modeled the proton as a perfect object, obeying the laws of symmetry, where we did not take into account the hyperfine structure, or we go into any more detail than that. And that's that for this video. Please do subscribe.